Okay, guys, let's go ahead and get started. So, exam one will be posted this evening on Blackboard, and all the instructions for it will also be posted. So, be looking sometime tonight for your first exam. So today we're going to start a new section on set theory. And so set theory, well, the notion of a mathematical set is fundamental to advanced mathematics. Most fields of mathematics can be thought of as a specific variation of some type of set. But what is a set? So definition. So a set is an unordered collection of distinct objects called the elements of the set. Okay. So, for example, we can have a set, maybe capital A, which is equal to the set consisting of the letters A, B, C, and D. Okay. So here, the members or the elements of the set A are A, B, C, and D. And we can write that using the notation that we've seen before. A is an element of the set capital A. Here also, B is an element of the capital set A. Also, we can use the notation an epsilon with a cross through it to denote that E is not a member of A. Okay? So sets, there's no ordering to the elements in the set, and they can have any number of things in them. In fact, you can have sets inside of sets. So let's look at some well-known sets. We have, for example, the natural numbers. So these are some infinite sets. And the rationals, or no, the integers, I mean. And then also the rationals. And we've encountered all of these sets before. Okay, so we can have finite sets, we can have infinite sets, just so long as all of the elements are distinct, meaning there's no repetition of elements. Those are called bags. And that's it. It's a very general idea. So let's get some more definitions now. So two sets, say A and B, are said to be equal whenever for all x in A, if and only if x is in B. Okay, so this is the biconditional operator. So this is true. So if x is in A, it better also be in B. If x is in B, then it better also be in A. So, for example, if two equal sets, say A is equal to A, B, and B is equal to BA. We're recalling that there's no ordering on the sets, the elements in the set. So these would be two equal sets because this is a tautology. So for any element, if you found that element in A, it's also in B, and any element in B is also in A. So these two sets would be equal. Okay. So another definition. So the set A is a subset of the set B written with the following notation. Whenever, for all x, if x is in A, then x is in B. Okay? So the definition being a subset. Now here, if A is a subset of B, then D is called a superset of A. A superset. A superset of A. Okay? And then this is true. So, for example, take A to be the set A, B, C, and B to be the set A, B, C, D, and E, right? E. So now, if we consider this this statement here, for all x, if x is in A, then x is in B, recall the conditional is true whenever, if that's true, then this must be true. Right, so if we pick something in A, any element, like B, for example, and then we look to the set B, that element is also in B. So here, A would be indeed a subset of B. Okay. Now, this this definition here is related to this definition of being equal in that two sets A and B are equal whenever they're subsets of each other. So another way of defining this definition here is to say that A is a subset of B and B is a subset of A. So when that happens, this implies that they're equal. Okay. All right. So let's continue. All right. So the empty set is the set with no elements. And it's written like this. Okay? Okay, so that's the definition of the empty set. Now I have a claim or proposition maybe. So if A is a set, then the following two things hold. We have I, so the empty set is a subset of A. In part 2, A is a subset of A. So what part 1 here is saying is that the empty set is a subset of every set. Okay? So I'm going to go ahead and prove part I for you. So, okay, so let A be a set. Then we just need to consider the definition of the subset. So then for all x in the empty set implies x in A. This needs to be a tautology. Well, this is logically equivalent to for all x. Now look at that right there. What's the truth value of this x element of the empty set? What's the truth value of that? Anybody?
False.
False, right? Because the empty set contains no elements. So with the conditional, right, this implication here, if you have a false hypothesis, what does that mean about the whole statement? It means that it's true, right? Anytime you have a false hypothesis, the conditional is going to evaluate it's true. So we've shown that this is tautology, it's always true, so we can just say, therefore, or something like this. So, therefore, the empty set is a subset of A by definition. So that proves part I. Okay? And a proof for part double I is similar. Okay? All right, so more definitions. So power set of the set A written with a script P of A is the set whose elements consist of every subset of A? Okay, so this is the power set. Okay, so let's look at an example of this. So if A is the set A, B, C, then the power set of A is equal to, well, by the previous proposition, we know immediately two subsets of A. We know that the empty set is a subset of A. We also know that A is a subset of A. And then what are some other subsets of A? Any guesses? Anybody? Someone take a guess.
AB.
So the set consisting of the elements A and B. What's another subset? Anyone else? Somebody. Just take a guess. What about the set with elements AC? What's another one? Somebody. BC, right? But, well, be careful when you say that. Say when you say it out loud, say the set with elements B and C. What's another subset? There's three left. That's a hint. So there's three other elements in here. What about the set with element A? That's a subset of that, right? What's another one? So now there's two more. Well, the set with element B, and then the set with element C. So altogether, those are all the possible subsets of A, so that's the power set of A. If you pick anything in this set, it will be a subset of A. That's the importance or the significance behind it. Okay? Now, for those of you that are interested in going to grad school, you can see some interesting power sets in some of your graduate level courses. For example, like you can see how many elements are here. There's 1, 2, 3, 4, 5, 6, 7, 8, right? Now imagine, for example, just like try to think about what this would look like. What do you think like the power set of the real numbers would look like? That's like, it's impossible to wrap your head around really, right? Like, there's so many real numbers, and every possible subset of real numbers would make up that set. So this is like a very large set. Okay? Okay, so we have a few more definitions. Okay, so an n tuple is an ordered collection of n items. So for example, most of you are familiar with tuples in the plane, the Cartesian plane. Well, an n tuple is just an n version of that, like a triple, right? Or a 5-element tuple, okay? So this is an n tuple. And an example of this would be something like so this is a, say, 4 tuple. So here, when we use the open parentheses here, this indicates that there's order in here. There's a first element, a second, a third. So this is not a set because of the ordering. So once we have that definition, we can define what's called the Cartesian product of two sets. So Cartesian product of the set A. My cat is bothering me. Of the set A with the set B, written as A times B is the set so A Cartesian product B is the set of all tuples AB such that A is an element of capital A and B is an element of capital B. Okay, so this is the Cartesian product of these two sets. Okay? So this is an and. So let's look at an example. Suppose A is the set 1, 2, and B is the set A, B, C. Then the Cartesian product of A with B is the set of all tuples of this form. So A, B, 1C, and then 2A, 2B, and then finally 2C. Now here, it's important to note that order matters, because if we look at the Cartesian product of B with A, then we're going to have a completely different set. We'll have this set. So A, 1, and then A2, B1, B2, and then finally C1 and C2. So these are different sets, completely different. They have different elements in them. Okay, so all of you have encountered Cartesian products before, in a sense, because you've dealt with the Cartesian plane, right? So if you have the Cartesian plane of xy, right? Any point in here will be an element of r times r. Okay. Okay. Now, the notion of Cartesian products can be extended. Um, so let A1, A2, dot, 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 AN be sets, then we can look at the Cartesian product of all of these. And this will be the set. So A1, A2, dot, 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 to AN tuple such that little a of I is an element of capital A sub I for I equals 1 to n. So this is a collection of n tuples now. So this now, if any of you have taken linear algebra, you're probably familiar with, so we look at three-dimensional space. Any point in three-dimensional space will be an element of r times r times r, which another way of writing that is saying r3. And another way of writing this here is to say r2. Okay. Okay. All right. What other definition am I missing? Oh, one more definition. So the cardinality of the set A written with two vertical bars around A is the number of elements in A. Okay. So, for example, A is equal to the set A, B, C, then the cardinality of A is equal to 3. So it has 3 elements in it. But you can also have infinite sets, like the integers, which has infinite cardinality. And then the cardinality of the power set of A here is going to be 8, right? We have 8 elements in there. But in general, though, the cardinality of the power set of the set A is equal to 2 raised to the cardinality of A. So maybe as like bonus on the first exam, we prove this as bonus. Yeah, I'll say something like 10 points or something on that. Okay. All right. So let's see. I suppose um, we can stop there for today. I know that this material won't be on the first exam, so I don't want to cover too much today. So yeah, I'll just end it there, and then I will finish writing your exam, and as soon as I finish writing it, I'll post it on Blackboard. All right? Okay. So hopefully everyone stays safe, and good luck on your first exam.